So welcome to my talk. My name is Martin Kolman, and I'm working in Red Hat in the Anaconda team, and we are doing the installer, the Anaconda. So yeah, the fourth one is the right one, but there are many other things called Anaconda, not only animals. So it's an installer. So every user of all these distribution which is installing it on some hardware comes in contact with it. This is what Anaconda does as an installer. It installs a Linux distribution to a computer, which might be just a blank computer fresh from the factory, but it also can be something that was already used and you are just adding a new system, replacing an old one. So there are quite many possibilities it has to handle when starting the installation. It needs to also correctly detect all the hardware, and because we are talking about normal, well, basically modular hardware, modular devices, there is a myriad of possible hardware which it has to work with. It prepares storage, which in itself is quite a major undertaking because there are many types of storage available even on normal PCs, and if you add some enterprise hardware, it gets quite crazy. If it has already, if it is running and it has some storage, it can use for installing software. It does the software configuration and installing because it aims to be able to configure as much as possible during the installation or as practicable, so that you don't have to do some time-eating configuring on all your computers after installation. And at the end, if everything went well and the installation succeeded, it will reboot the computer and it should then work normally with a new operating system. What Anaconda actually supports as a computer for running the installation, of course it runs on normal x86 personal computers. So what most of you have, like a notebook, like a desktop workstation. It also needs to run on servers, and because it's supporting the Red Hat Enterprise Linux, which is used quite heavily in the industry for mass deployments. It can be either thousands of workstations in some company or some server farm data center. So it needs to be able to scale and to be able to be automated and to run in these mass deployments on many machines. It also has some initial support for the ARM architecture, like, for example, the Raspberry Pi or the BeagleBone. Also, it supports the PowerPC computer architecture, which has also its own specifics. And quite an interesting addition, it supports mainframes. It still supports the IBM S390 mainframe computers, where you can also run Linux. So Anaconda does the Linux installation. It's really mainframe stuff. It still has basically something like a virtual typewriter for console. Many stuff you are accustomed to is just missing there, so it's quite fun to support it. Storage, I've already mentioned some of the funny stuff. And even with the basic storage, there are many interesting challenges with nested LVM setups with Btrfs. There are many issues with it that we are working on because it's quite complicated. And the funny stuff is enterprise storage. There are very special devices used in data centers for connecting to storage by independent paths, so that you can have multiple ways to the storage device. So you can overhaul some of them and still be connected. And so you need to be able to connect to storage remotely. Actually, you can even install on this storage without having any storage devices on the device you are installing on. So, and Anaconda needs to handle all of this. So if you are installing Fedora to your laptop, it needs to work. And even if you are installing in some data center on a iSCSI block device and you are creating a RAID on it, and you are creating LVM on the RAID, and on the LVM you are installing Btrfs, it needs to work. There is also another issue Anaconda needs to handle, and that's the rapidly changing landscape of community-developed Linux distributions. Anaconda is the default installer for the Fedora distribution, which is developed by the Fedora community, and it's in quite a rapid development. The project aims to be hosting all the newest technologies and testing them out and deploying them so they can be tested and stabilized. So the end result is that Anaconda has to handle all these changes. For example, we found out after getting some bug reports that the hostname just depreciated some of the often used switches, so it crashed. Also, we are using the GTK graphics library for the user interface, and we found out that one day it just started to call system exit because, yeah, no X server is running. We were using it to check if the X server is running. It just called system exit. So that was an issue. Also, one day the directory used for storing temporary data was moved to a RAM disk. So if you store too many data, like we were storing their installation packages before installing them, we run out of RAM and that's it, because we have no swap during installation, because we are still configuring the storage devices. So this was another issue we had to handle. So actually, I've mentioned it's an installer. So how does it work? Anaconda has about 2.5 ways of installing the operating system. The first one, it's the interactive installation. It's just an installation wizard that starts and guides you through the installation. You can configure the system, how it would be installed. You can select packages. You can configure which keyboard layouts will be installed, which language will be used for the system, which localization settings will be used, time zone, and many other options. And then you just start the installation, and Anaconda will then handle everything itself. And Anaconda can also handle everything itself. In this non-interactive mode, it runs without any user intervention because it's configured by the so-called Pykickstart recipe. Pykickstart is probably a topic for its own presentation. It's a very powerful configuration language which you can use to specify basically almost all you want to ever configure on a system, like partition layouts, all languages, time zones, network settings. And it can also have scriptlets in it, so you can also include small scripts in it that can fetch data from the internet. So the possibilities are quite endless. And with such a recipe, you can just load it to the Anaconda, for example, from the internet, or include it in an installation image, and everything will be automated. You'll just come to the device and it will be already installed and running. This is what's used for the mass deployments, because Anaconda can also do installations from PXE. So you just set up a PXE boot server on this server farm, and the machines will automatically boot from the PXE server, start the installation environment, and everything will be installed according to your Pykickstart recipe. And there is the second and a half one, the option, and it's a hybrid installation. Because actually the installation is using a special tree data structure, which is either manipulated from the UI or generated from the Pykickstart. It's basically like a modified nested dictionary. And this dictionary can be pre-filled from the Pykickstart. So you can, for example, pre-fill the time zone and just configure the storage. So this is the current Anaconda graphical user interface, and we have nice music backdrop. It's currently, as you can see, this is the so-called main hub. The Anaconda is currently using the so-called hub and spoke topology. This is a hub, and all these buttons are so-called spokes. The users can enter, configure what's needed, and go back to the hub. Once everything is configured as needed, the users can start the installation, and again, this is everything else is then automatically until restored. This is an alternative text-based user interface, while the graphical one can be also used either directly from a device which has a screen, but it might not have a screen like many servers do. And the graphical user interface can be also used from through VNC. But on some machines, even this one won't work. So we have the text user interface, which again has the basic hub and spoke topology. Just only that the spokes are like, it's a text. And it has also one quite important feature. It's a so-called write-only graphical, write-only interface, because we need to support the mainframes from the series 3990, and they basically just emulate a mechanical typewriter. And typewriters can't really rewrite what they've already written. So this GUI is made so that it never changes the terminal in any way. It just adds more lines. So it would work quite nicely on a typewriter, for example. So the Anaconda project is actually quite old. The first commit for the graphical user interface of Anaconda comes from 1999, but the non-graphical part of Anaconda is probably much older. And the important thing to know about Anaconda's history, that the project has been developed from 1999 continuously up to this day, and has been used for all Red Hat Linux, Red Hat Enterprise Linux, Fedora Core, and Fedora releases since then, and for any derivatives, because Anaconda is an open source project, and Fedora and Red Hat Enterprise Linux are also open source. So there are some derivatives, and they are of course also using Anaconda, because that's the main installer for the project they are derivating from. There are some short statistics from the basically mostly generated from the project source code repository. It's not as big as, for example, Django, but it's still not a small project. There are quite a lot of people working on it. Currently, basically, for example, from the core team working for Red Hat on Anaconda, there are 3 guys, including me, in Brno. And the rest of the team is in America, about 7 to 8 people, mostly located on the eastern seaboard. It's a pleasure, and you can actually meet them. I had the luck to actually meet my boss, but my coworker, he was working 2 years on Anaconda until he met him for the first time. So yeah, it's like this when you are working on a distributed project. So also, basically, I'm mentioning the Git repository, but the first version control system used by Anaconda was CVS, and it was imported. So it's actually quite big. So if you are just cloning it for the first time, it takes some waiting. So, well, actually, we are on a Python conference, so I really should talk more about how Anaconda is using Python. We're currently using Python 2.7, like for example OpenStack. Because Anaconda is not really imported from other projects, we can basically one day decide we want to rewrite it or to support Python 3 without really thinking about backwards compatibility. So this is planned, but for now we are just using Python 2. For the graphical user interface, Anaconda uses the GTK3 graphical library, which is used, for example, for all GNOME desktop environment applications. We are using the G-object introspection interface, which enables all libraries that use the G-object object system to provide bindings for other languages. So, like this, we are accessing the GTK, which is using the G-object object system. The layout of the graphical user interface is specified by XML files, which are generated by the Glade interface designer. It's some quite ugly XML, and it's really nice if you get a patch for it, so you just see a lot of, yeah, this number changed there, and this attribute now has an underscore. We have also some custom GTK widgets, which are basically the only C code that's in Anaconda. So basically, if you are building Anaconda, you just have to compile these widgets. The rest is Python, so you don't have to compile it. And the text user interface, in earlier versions, we were using the Nude text widget library. But for this new UI, we haven't found anything that would satisfy the write-only requirement. So we have some very simple widgets that only add lines and generate stuff without rewriting itself. Regarding the architecture of Anaconda, it's an application. If it's running in the interactive mode, it's an application that's interacting with the user. So we really need that stuff that takes long is running in threads, so that the user interface is always responsive. This is double so important when people are using virtual machines, when they are using VNC over some long latency links. We really need it to be as responsive as possible. And so we are using threads, of course. But the problem is that many of the libraries Anaconda is using and needs to be using without much alternatives being available are not thread safe. GTK is not thread safe. Even the dbus bindings we can use are not thread safe, and we need to work because we are configuring networks through them. We are interacting with the systemd init service and many other important things. And even the package manager, which is installing the hundreds of packages that are installed by in normal installation run, is not thread safe. So we had to do some. Yeah, it's quite difficult sometimes. For example, this is how we handled the GTK not being thread safe. The problem was stuff running in threads needs to tell a GTK to do something, and it can't call it directly because you can end with a freeze, or it can just segfault. It might even get some error messages from the X server and freeze. So this is one of the solutions we are using. Basically, you just need to decorate a function with the GTK action no wait. We have also a GTK action wait, and this function call, either if it's no wait, is just submitted to the main thread to a queue, and the main thread is basically, it's a consumer, it's consuming from the queue, and it just calls the function when it wants to. And there is also a wait variant where it actually the call is forwarded to the main thread. The main thread processes the call and actually returns the result to the calling other thread. The thread is just waiting for basically the decorator makes sure that the calling thread is waiting for the queue, the output queue. So the main thread has two queues, one input queue and one output queue, and you're just basically taking part of the execution of another thread, move it to the main thread, and then return control back to the calling thread. We haven't really seen it anywhere else, so I thought that it might be interesting to note this. Also, from the need for managing threads, there was a need for really a thread managing module, so we made our own. All threads are started through the thread manager, so you can log them when they start, when they finish, or when they have an exception in it. Also, it's easy to check if some thread is running, because all threads have unique names. We can track, and we can also wait for them. So, for example, some threads are waiting for the network connectivity thread because they need internet connectivity, and they can't really do any work before they know either that we are connected to the internet, or that we have no internet connectivity. So they need to do some either do nothing or use some backup action. Also, there is quite an interesting behavior in Python in regards to threads. It seems to be having some issues where some exceptions end. If I'm not mistaken, for example, where the user presses some keyboard interrupt buttons, the keyboard interrupt exception can actually end it in any Python thread. So we're using the thread manager to forward the exceptions to the main thread, so they can be processed in some way, and don't end just in some thread. There's this unique making something completely unrelated. So Anaconda is quite a big application, so we need to be able to debug it effectively. It's a big difference from an application that's running, for example, Firefox or some desktop application, because if this application is not working, the user can't use the application. But if the Anaconda crashes or is not able to install or on some hardware, the user is not able to use the hardware because it has no operating system on it. And the hardware can be a personal computer or also a server farm. So it can be quite an issue. So the most basic debugging tool is logs. Anaconda has a main log file, which is used for the miscanthus errors it's getting, or it might be getting. And it has also special log files for storage. It also logs all programs it's running. So this can be used, for example, for spotting programs changing their API, because you'll get some errors in the program log. There are also some logs that are actually present only during installation, because they include sensitive data. For example, Anaconda does geolocation, so it can use your IP address to preset the language on when the installation started. And this is quite a sensitive information, the information about your current time zone. So it's stored only in a file that's not copied to the installed system, because this is also a useful tool, because a failed installation might not really produce a non-booting system, but there can be some issues. And these files are copied to the installed system, so you can check them out and see if there were any issues during the installation. Also, when the installation is running, there are multiple TTIs on the TTI number 2, there is a bash shell running, so you can just inspect the system, read the files, use SSH to other machines, SCP, the logs, basically anything you can use from a shell. This is another option. If Anaconda really crashes, if an exception bubbles all the way up, this is the Anaconda exception handler. This is a bit related to a talk about debugging application earlier, because this is doing something, it's handling basically something like an idea that was mentioned during the talk. Because the exception handler, one of the things it does is that it dumps the Anaconda object tree. It basically starts on the main Anaconda class, and it recursively dumps all objects and their properties to a text file. This text file is then stored in the log folder, and you have the option to report it as a bug, and it can be either automatically added as a bug report to the Red Hat Bugzilla, or it can be sent to some, you can enter SSH login information to a server, and it will be transferred to a server you can use to analyze it. Also, there is a debug button that makes it possible to use PDB directly on the spot where the exception was raised. So I basically mentioned most of this. Anaconda is an open source project. It's licensed under the GPL in version 2. And the workflow we are using is quite simple. Developers or community contributors all send patches to a mailing list. The core Anaconda developer team reads the patches, applies them, tests them, and acknowledges them or has some remarks to them. And once they are iked, they are pushed to the Anaconda Git repository by the core development team, which have Git push access to it. Anaconda needs to support multiple distributions, the Fedora and also the Red Hat Enterprise Linux. And so once such a distribution is released in a major version, we make a branch, and this branch is maintained and bug fixed until as long as the distribution release is relevant. So we are currently supporting the RHEL 5 and RHEL 6 Enterprise Linux releases, and we are still fixing bugs in them. For example, RHEL 5.10 was recently released and is still supported. The Anaconda project is running for quite a long time, and we have always seen a tendency that some subsystems that were just built-in modules in Anaconda, just part of the project, they grew as we added new features, improved them. So periodically there will be parts of Anaconda that will be split out as a separated library, so that we have so it's more modular, because you need to have an interface, stable interface to these modules, and also that they can be used by external projects, which has the added benefit that more people can be working on it, more patches and more testing. One of these split libraries is the Pykickstart module. It's a handler for the Kickstart configuration language. It does Kickstart parsing. It's using, I think, opt-parse currently, and it takes the Kickstart text file as input and passes it to command class instances. The commands are Python classes, and we use inheritance if a command gets changed. So if you're adding or removing some options, depending on the current Fedora release, it gets a new version represented by a new class. That subclass is the previous version. So you still have all the old versions available, but you just use the latest one when you're using the latest distribution. Also, Pykickstart does validation for Kickstart, and that's an important feature for Anaconda. It can regenerate the Kickstart file from the internal tree Kickstart data structure used in Anaconda. So if you change something, or even if you're just doing manual installation, at the end on the installed system, in the root folder, because it can be sensitive, it can contain sensitive information, there will be a Kickstart file describing all changes you did in the installer. So you can both use it for debugging or install an identical system, like the one you've even manually configured. The second most important split module is the blivet. It's called it's handling storage, so it's called like an impossible object, because handling storage can be demanding. It needs to handle a big lot of storage devices and file system and all their combinations, so it's quite crazy sometimes. I've been recently adding the TMP, temporary file system support, and yeah, it was interesting. It has a test suite that's making partitions, mounting them, formatting them, removing them. So it needs to run as root, and it can be quite an adventure to running it on your system. So, but unfortunately, there is no other way to really testing if the utilities are actually formatting the partitions, moving them, resizing them correctly without really running it. This is the module that does the Python object tree dumping. Of course, it's also an open source project. It's available for Fedora. There is a Git repository. So yeah, and of course it can be used anywhere. It's used by Anaconda, but it's a separate module. So if you want to dump your project in case you have some issues, some exceptions, you can use it. And we'll be glad if you use it. Also, the preparted was born from Anaconda. It's Python bindings for the parted partitioning library. And I think this is the last one from the Anaconda children. It's the lang table project, not directly born from Anaconda, but it was born from the need for better localization. The lang table project is quite simple. It's a set of tables that have weighted values for various localization bindings. For example, if you want to get a language for a territory, because you got a territory code from GeoIP, you get a weighted list of languages. So, for example, for Britain, you'll get English, followed by all the smaller dialects. Previously, you just got a list of dialects and English, so you will be getting some Gaulish dialect as the first one, because it was first one by the alphabet. So it fixed quite a lot of issues. And again, might be also a nice addition for improved localization in some other project. So I'm slowly getting to the end of the talk, and so it's the obligatory future plans slide. Well, these are our future plans. There are plans because you really never know what new features might show up, what new projects speed up, what projects are delayed, and we need to follow the development of the Fedora distribution, so this might change. But currently the Fedora plans to both introduce Python 3 as the main Python interpreter and also introduce Wayland. Anaconda has basically a small Fedora distribution it uses to run and to do the installation and startup. So we might do also a conversion to Wayland. We're currently using the X server for graphics. And the Python 3, that might happen quite soon, actually, maybe even the next or over next Fedora release, which might be in a year, for example. There is still already some preliminary work. Yeah, we want to improve the documentation, or more importantly, have some documentation and add more tests. There's one colleague is actually working on so-called cloud tests, and the idea is that he will be running installations with slightly different parameters on cloud instances, on some cloud virtual machines, basically single-use ones. And like this, he can really test partitioning, changes to the virtual hardware, which wouldn't be really possible to run just on a workstation, because you don't really want to let Anaconda remove all your partitions and replace them with LVM installed on RAID with Btrfs on the top. And this is all. So if you have any questions, well, I'm prepared to answer them.
So you mentioned that you are using C to implement widgets. Mm-hmm. So do you think it would be possible to try to implement a GTK widget using Python by creating some, some code that can just go back to Python?
Yes, it should be possible. The same stuff we are doing with C should be possible to be done also from Python. Basically, some of the widgets were basically imported from other projects. For example, the time zone map project. I think it has come from some GNOME project actually, and so it's quite complicated. So it's something that's running. We still have to build the Anaconda, generate localization, stuff like this. So the edit compile step is not a problem for us. So yeah, the only issue I think that might be there is the only issue might be with speed on some slower devices or over VNC, because still the Python overhead for like drawing stuff with Cairo might be bigger than using C. Also, some of the widgets might be quite old. There used to be a stage 1 part for Anaconda that was written in C, so it might have some old roots. But I think it would be possible.
Okay, thanks. And could you tell maybe something about whether are you using callbacks and GTK callbacks for reacting on for example, on a click on a button?
Yeah, we are using callbacks.
So how does it work with a multi-threaded application?
Basically, we have a message queue. So I think it works. Basically, we have a main thread which is allowed to work with the main loop, with the Anaconda, with the GTK context, and I think we might be using even the decorator I've shown there. So we just make sure that either it's running only in the main thread, or if that is properly decorated, or it directly sends a message like button XY has been clicked, main thread, do something about it.
Okay, so is it broadcasted to all the threads, or do you have some system to say that this button is handled by this thread?
I think it's more like it depends. If the button needs to change something on the GTK context, it needs to send a message to the main thread. If it just needs to react on it, it shouldn't be any problem, as long as it doesn't interfere with the GTK stuff.
Okay, I get it. Thanks.
So, thank you very much.